Okay, we are within the town of Negaunee, Michigan. That's US 41 here in the background. And today I'm going to take you on an outcrop I've already taken you before, but we're going to do some structural geology. But first I want to talk about the lithology real quick. I'm just going to get it out of the way so we can get the structural part moving so this video isn't too long. Basically what you are going to see is the Negaunee group, like we did at Iron Mountain, except at Iron Mountain you had the older Felch formation and the younger Vulcan formation. Here you don't. It's still part of the Negaunee group, but you have the Azurbajic quartzite, which is the oldest. Then you have the Siamo slate, which is equivalent roughly to the Felch. Then you have the Negaunee iron formation, which is lithostratigraphically equivalent to that Vulcan iron formation at Iron Mountain. However, if it's chronostratigraphically exactly equivalent, we don't really know. But it is going to get noisy down there, and hopefully you'll still be able to hear me. But I just wanted to get the lithostratigraphy out of the way as we look at these rocks. Okay, now I'm going to take you to look at these rocks close up, and the reason why I'm doing that is I am not a fan of doing remote geology where you can physically look at the rocks, because you can misinterpret things. There's a lot of things we can do, like magnetic surveys, aerial surveys, LiDAR surveys. We can even look at Google Earth. But when we look at this rock, and it's actually low-grade metamorphic, but I didn't tell you what this was, if you're just looking at Google Earth, you can totally get it wrong if you had no idea what was here. This is the northeast end of the outcrop. And this rock here is part of the Siamo slate. But it doesn't look very slatey, does it? Well, it is here, but this is actually what we call gray-wacky. This is a very lithic sandstone. And that's what we're just going to call it for now. It's a little more complex than that, but these are talks for other times. So we're going to call this thick unit here a gray-wacky, and this is a slate. Now, we're not going to get into the bedding yet because I want to take you just a little bit this way. Okay, now you can see more of the slate. Now, if you were just looking at Google Earth, looking at this rock outcrop, and you had no idea where it fit in geologically, you see these here, this here, you might think that's some sort of dike. But it's not a dike, it's that gray-wacky. So this is all sedimentary. Well, it's protolith, or parent rock is. Like I said, it's been metamorphosed, low grade, and you can tell by this that our bedding, that when this was, deposited horizontally, it has since been tilted, and this is a bedding plane, and this is a bedding plane, okay, on our gray-wacky. You look at this rock, you can tell it's not igneous. And this definitely isn't igneous. And this is our slate part. Now you look at it and you see these lines, and we're going to talk about those lines here in a minute. But those lines are not bedding. And you can tell that these lines are not bedding because you can see there's a little bit of banded iron formation or biff in this rock. You can see that this is bedding. That's a bedding plane, just like this is a bedding plane. And you see these too, and I'll get into those in a second too. So this is more of that gray wacky. So we know this is bedding. Bedding goes this way. All right, it's not this way. So let's talk about these lines here first. Those are what we call fractures. Fractures are breaks in the rock, joints are fractures, stuff like that. It doesn't have to fit a pattern, although it usually does. But those aren't the important part here. I did measure these, but I don't think they mean much. What is important here is this stuff. these lines. And I said, this is your bedding. And the trend of the bedding here is mostly east-west. It's not exactly that, but we're going to go for it here. I have been taking notes, and I did detailed notes here, which I'm going to show you in a little bit. But this is your bedding. So what is this? Is it fracture? No. I've called these foliations before, and that's, depending on who you ask, that is correct. But they're technically cleavage, a specific type of cleavage called slaty cleavage. Slaty cleavage are foliations. Foliations are just where minerals have aligned parallel to each other or subparallel. Slaty cleavage, and there's different types, so we're only going to address that one, is also that definition of foliation, except this trend, so this weakness, this zone of weakness where this is breaking, follows an axial trend of a fold, as where fractures do not. What do I mean? Well, this cleavage here is also almost east-west, but it dips far more steeply than our bedding. That's about our bedding. There's our cleavage. So, and there's basically two types of folds we're going to talk about. We're going to talk about anticlines and synclines. That's basically, this is one of those. An anticline is when you've taken level rock and folded it so essentially it bows up, and the axial plane would be here. A syncline is the opposite, where it bows down, but your axis is here. So it's in the middle, relatively. It's actually in the nose of your fold, the point of your fold, trending up through your fold, following a trend, all right? It follows the cleavage in this case. But in other cases, it's oriented to the nose. So how do we know if we have a syncline or an anticline? This is that cleavage, and I've shown you Pierce Gorge, and that is cleavage is pretty close to the bedding plane. So you can have cleavage along bedding as well, but here you don't. Bedding, cleavage. And the cleavage is very consistent. It doesn't change, although the dips of these do change. These may have the same trend, but the dip changes from about 45 to 65 degrees. Before I start answering whether we're in a syncline or anticline, I want you to look at this real quick. This technically is a gray wacky like the rest of it, but look at how it weathers. It weathers more brown. You see clasts of the slate in it with this quartz layer. Technically, you could call this a gray wacky, but I think, and I need to look at it petrographically, I think this is a tuff. I think this was laid down on the slate as a volcanic tuff. So it's not a true gray wacky. And technically that would make it igneous, but it would have been on the bottom of the seabed. And I think that's partially why it kind of bended easier than most of the gray wackies do, and the fractures are close to what they are in the gray wackies, but not quite. But then you look at other parts and it looks like a gray wacky. So it's kind of hard to tell. I need to do petrographic analysis, but tentatively I'm going to call this a tuff, although it could be a gray wacky. Okay, here we're going to answer our question. We are in the limb of a syncline. A limb is an arm that spreads out from the nose of either your anticline or your syncline. How do I know we're in a syncline? Well, we are making a geologic map as we go along. It's just I haven't brought it out here with me. But you start coloring your map and putting down your strikes and dips because geologists get to play with colored pencils. You're going to make a geologic map. We aren't going to do it exactly how you would do it, you know, in order to produce a professional map, because we don't have the time. We're just going to spot do it. There's a couple of sites on here only that we're visiting. Normally what you would do, as you can see, here's your base map. It's a topo map in this case. There's a contour interval. There's your scale bar, north arrow, and here I have some boxes. This is where you would color in any units you find in the field. The colors don't really matter. There are standards, but this is a field map. You can make them whatever you want, as long as they're not too similar so they don't stand back to back, and you know, like you don't want an orange and a red orange because you might get confused later which is which. So what you would normally do is you'd walk the area. See, these hills are probably outcrops. This is an old mine, and you would come across this, and if this was a banded iron formation and you're using red for your banded iron formation, you may or may not know the units. It doesn't matter. If you do, you write the name. If not, then you just wait till you get back and try to figure it out. But let's say you don't know it. This is a BIF, banded iron formation, and you say you'd color that red, and this is a BIF, and this is a BIF. You'd also write your geologic symbols on here, strike and dip, foliations, anything like that. Let's say these are just your outcrops here, and this is BIF, and you can't see in between them. You can just color it straight across. That's the law of lateral continuity. All right, so, and what you would do is, you know, or you can wait till the very end. You have all your colors in at the outcrops and all your measurements, and then you fill in the blanks. If you see a contact, you draw a line there, a solid line. If you can't see a contact, you can extend it, draw it dashed, something like that. But we're just going to visit a couple spots, so I'm just going to show you the basic beginnings of how to draw a map in the field. I'm not going to go through the actual in-depth entirety of doing this. Okay, but how do I know or strongly suspect I'm in a syncline? And this is one of those things in geology where geology can make predictions. All right, it's not just looking at rocks going, that's a slate, that's a great wacky, ooh, ah. You can actually figure things out and make predictions and extrapolate units in the field. But what you see up here, this fold, and I've studied this before and looked at this before, this is an expression of what we call Pumpelly's rule. You see the way the folds form in the slate. Pumpelly's rule basically states that you can have the larger structures that you can't see on the ground reflected in the smaller ones. And this is one of those smaller structures. Now you look at it and you can see the limbs, and you see a syncline, and you see another limb come down, then it gets complex. And it gets like a little anticline, but it could be faulted, stuff like that. And we're gonna go to that place at the end here, and I'm gonna show you how complex that is. But if you look at the left side here, this one limb, the dips of the limb are very consistent with the actual dips I've been recording. Strike would be, this would be a long dip. This is a cross section, a long dip, all right? So strike is this way, okay? So it's perpendicular to strike. So if this is an example of Pumpelly's rule, and we are on that limb on the left here, because our dips are consistent with what I've been measuring this whole time, if we go to the northeast, which to the left, that way, well, to the left of the structure, but to my right, we go to the northeast, we should see older units. Maybe that Ajobizic quartzite. I hope I'm pronouncing that right. I have no idea. So we should see that. And if we went this way, we should see younger units like the Negaunee banded iron formation. We are about right here. Okay. Now, I'm using this color, and I'm going to put this right here, and this is going to be my Siamo slate. Now, I'm just calling it the slate. I know there's numerous lithologies in there, banded iron formation, slate, gray, wacky, and possibly some tough, but if you look at our scale here, this is 1,000 feet, and our outcrop is basically right along here. Now, some of those beds are less than 3 feet thick. Some are about 8 inches thick. Now, at this scale, there is no way you are going to be able to map those. Remember, when you're mapping, scalability matters. So we're just going to map it as one unit. Also, I have my strike and dips. Now I would normally do this with a compass to get it good. This is just to show you guys what's going on. So we're not going to do our cleavage on here yet. First we're just going to do our basic strike and dips. And they're essentially, they're not exactly, but they're essentially east-west, okay? And then we have a dip this way, and they dip from about 45 to 60 degrees, so we'll say about 55 for most of them. Our cleavage also forms in the same direction, almost east-west. We are going to map it like we can't use the strike and dip symbol, so we are going to use this symbol. We're just going to do this, and it also dips to the south, but it's about 75 degrees. It's a little more than that. So it dips steeper, the cleavage, than our bedding. Now some of the beds do turn a little and stuff like that, but that's basically how you would do this right here. Now, according to Pompelli's rule, if we go up here, we should find older rock, and that's what we're going to do next, and then we'll fill out our map as we go. Okay, we're at the southwest end of the outcrop, or west end, and here you can see we're back in a massive gray wacky with slate beds in between. And I'm going to show you real quick how I've just been taking notes and how I went through this already, but I just want to show you what I did in my notes real quick. You can see I have a title, date, people who are here. Then I have the GPS of the east end. It's actually the northeast end of the outcrop. And then I have my pictures log that I took with my phone. And then here I did a 2-scale cross section. Okay, and I have my strikes and dips on there. I have my cleavages on there and my sample locations, and there's the legend for it right there. Okay, we've come northeast of the last outcrop. You can actually see it way down there past that stoplight. That's where we came from. And here you can see yardstick, mile marker 123, 123 right there. But here, now we've come northeast, and if our prediction that we have a syncline is correct, this should be older. Azure-Bajic quartzite, most likely, possibly Mesno. And we come this way, so this is older, and I have done measurements already. This should be the oldest stuff at the outcrop. And we get younger as we go that way, as we get towards our other outcrop down there across the lake. So you can see this here. Looks like a pretty clear quartzite. And it is. It's what it is. It's a quartzite. Come this way, you can see what might be bedding planes. Could also be a cleavage. You can get cleavage in quartzites too. But we'll answer whether or not that's a bedding plane here in a minute. If you come this way, you can see the quartzite's pretty white. And then you keep coming this way, it's still white. And you can come here and you see these structures, which are secondary from water around that fracture. That's a fracture right there. That's not bedding, but, well, it could be. We don't know yet, right? But we come this way, and you can see the quartzite starts to take on a grayish and a green color. And it gets really gray and green, and you start to see other things in here. The quartzite becomes much finer grained here. It's pretty much quartzite, but it's mostly silt. But the silt is made of quartz. And so you start to get banding in here. So maybe this is bedding. And you look here, and you see granules, which means, since this is sedimentary and deposited relatively flat, you know, the law, original horizontality, this has to be a bedding plane. You can see these white granules, even though this is pretty featureless. So this is a bedding plane. So our bedding is here, but we have to be careful. Quartzites like this like to be cross-bedded. And I took measurements, and the cross-bedding here is actually minimal. It is pretty much on strike with our Siamo slate. That almost east-west and dips towards it, towards the south. But how do we know this isn't overturned? Well, come more this way, we get more and more greens and grays, and you still see it's mostly still dominated, but you come up here and you see ripple marks. And this is the top of the ripples right here. this is the top. These ripples are the top. So our top of bedding is towards our slate. So we do pretty much have a syncline here. As long as we have no other major weird structures between us and that Siamo slate, like faulting or complex folds. But since that little miniature Pompelli's rule folds seem to predict this accurately, we have no reason to believe there are anything like faults or complex mini folds in this. So this should be the same limb of our syncline as our Siamo slate is. And you come here, I just want to show you this real quick, and you see these spots. Now, this isn't from the snow or rain, and it's not from, sometimes when they asphalt these roads, they'll kick it up, and you get tar on here. That's not it either. I actually took a sample of this because I don't know what it is. It's got to be some sort of concentrated mineral, could be from being metamorphosed, because we do have a quartzite here. But from this point, we are going to go see if Pompelli's rule holds in the other direction, past the slate. We're going to go to the old Jackson mine, because that's probably the best outcrops around here. Now, there is more quartzite behind the truck in that cliff down there and on the other side, but that's been mapped as Mesnard. Where the truck is, just behind it is a valley, which does seem to represent a fault. At least that's how it's mapped. So I'm going to finish up our little geologic map we've been making for this stop, and then we're going to go to our third and final stop. Okay, so there's our Siamo slate, and up here is where we were looking at that other quartzite, which is the Azerbaijan. So we're going to make that orange, and we know that's older. Now, obviously, you know, this is field use, so it doesn't have to follow any particular rules or anything. Just, you know, your oldest stuff down here, your young stuff here. And Azerbaijan, I think. I don't know if that's how you spell it. But anyway, up here, you come up here, and let's say we had about the same trend. And our dips like that. The dips were, they're a little steeper than there, more along the lines of the cleavage, but they're about 75. What that means is our syncline, this is a limb, so we should have the axis down here somewhere, maybe even further down. Now we are going over here off the map. Things get complicated down here. There aren't very many outcrops, very good ones or ones at all, and you get igneous intrusions and stuff like that throughout the Negaunee. So we're just gonna go, and I'm just gonna show it to you, and I'm not on the map anymore. But this syncline does have a name. It is the Eagle Mill syncline. Here's the geologic map. Here's our A to A prime right there. So there's our A to A prime, because for some reason on these old maps they can't do that from left to right for some reason. That's just, they all do it that way. So our first outcrop was here, and this is all the Siamo. Second one was here. Remember I mentioned the faults, they're up here somewhere, but there's our second one. So our synclinorial axis, and as you can see, you start to see these intrusions. This is the Negaunee iron formation, which we're going to look at, and you can see the syncline gets complicated, and there's other faults and stuff. Axial plane of our syncline, which is usually done in red, just for what you can see on the map here, is about right here, okay, which would put it right about here on the map. And you would do this or that. So on our actual map, business 28, our synclinorial axis is right about here, east to westish. And you put arrows towards it. Since it's syncline, if it was an anticline, the arrows would be going away. So it's about where our axis is. All right, so let's go look at the Negaunee. Okay, we are away from Teal Lake in US 41. We're southwest, well, more westish, but southwest of our Siamo slate, our very first outcrop. And it's a lot more quiet here, and it's snowing a little bit, but we got clear blue skies right behind us right there. Hopefully the sun will come out. But here, I want to show you some of this before we get into the rocks. This whole area is an old mine, the Jackson mine, and they have put some of the stuff out here, some of the equipment used during the mining of the early 20th century for you to look at. We're not going to focus too much on this, but I think it's nifty to show you it. There's a bucket with some ore in it. It's actually just random rock, but this is what it would look like. Here you see a little bit of about the Jackson mine. We're going to pass this pit. It's not a very big one. A little bit of information about the trail. It's a piece of art. It shows the miners actually doing double jacking. It was used, what they would do before machines is they'd pound posts into the ore, pull them out, and stick dynamite in there to clear it out. And we come this way. I actually don't know what this is right here, but it's pretty cool. There's no sign on it, at least not that I'm aware of. Here's old rail cars for transporting ore. And people. This is one is for people. This isn't one for ore. These are for ore. Now we're just gonna go along the trail for a little bit. I'm gonna show you some of the complexity of the banded iron formation here and the problems that we have. So what you've already seen is, remember, we had the Azurbajic quartzite, which was our second stop. So we're on the limb of a syncline, then our Siamo slate. So we should have Negaunee iron formation here, and we do, but we're not going to find the axis of that fold because the fold has been complicated by faults and intrusions and stuff like that. And that's even kind of reflected in that piece that was a bit of Pompelli's rule. You see that on the down part of the limb. It looks like it's a complex mess. When you start coming this way, this is all banded iron formation here. You can see how messy it looks. This rock changes orientation a lot. It's not consistent. You get stuff that looks like mini anticlines right here. You can see this comes up this way. Comes up, this would be your limb of an anticline. It comes up to about right here. That would be your nose up there. That would be your axis. Okay? And then it comes down this way. Alright? So that is a little anticline in here. But then you come here and it's gone. You lose it. It's just, so you have a lot of complex stuff. There's likely a lot of little micro faults. Not micro faults, but human scale faults. Faults with offsets of maybe 10 feet, you know, stuff like that. And in other places, the iron from the BIF, when it was being deposited, was in relatively turbulent waters. So you don't get very distinct bedding in places, although the bedding here is about right here. But it's hard to see. You can see the red jasper and the hematite or some other iron mineral like that. So you know this is the bedding here. What's this dip? 30 degrees maybe? And you come just right here, and the dip's 45, 50 degrees, and you're still on bedding because you can see the beautiful jasper and hematite in there. And you come this way, and we should be on top of the beds here. And you can see how undulating this is. It's not really level. It's very uneven. And this would be the top of the beds, at least those beds right here. You come this way. This was the first open pit mine here. This is what I originally showed you on the way in. And it's filled with water now. It's just a little bit of information on it. So you can look at it and see it's filled with water down there. They don't want you down there. So we come this way, and the top of our beds are right in that face there, off to the edge of the cliff. We come this way. When you get here, we're not that far. I mean, the top of the beds were there, the open pit's right there, and this here, and you can see bedding's really hard to tell, but you can tell this is not the top of bedding right here. You can see the complex, look at, you see these mini folds, anacline, syncline, anacline, broken, faulted, other jasper in here. This is all jumbled up. So the bedding plane is hard to find here. Bedding probably is right around here somewhere. Like this face is probably bedding, but quite honestly, it's really hard to tell. So as this was being deposited on the bottom of a sea floor, we do know other stuff was going on. We had igneous intrusions coming in. This was probably already being deformed, you know, into other structures as it was being deposited, and possibly even faulted. Faults that form during deposition are called growth faults. So this thing was undergoing change as it was still being deposited. Remember, this is the youngest of the Menominee. The oldest was the Azurbajic quartzite, the Siamose slate, it was in the middle, and then Negaunee is the youngest. You can also see here how this was all quarried out as well, and they left a lot of talus. Some of this has subsequently fallen post-mining, but they went back in there from the initial pit, which is right here. So this rock here is not simple. Okay, so now that I've shown you what I wanted to show you in this, which wasn't really lithostratigraphy or stratigraphy, I wanted to show you cleavage and how we can use structures in the field to make predictions about what we will find, whichever direction we decide to go, what we think we will find. And that kind of methodology is what's used for finding stuff like this, mineral resources such as iron in this case. Like I said, you know, here it's a little more complex, so we're not going to add it to our map or anything like that, and it's not as easily deciphered. But we do know that we were on the edge of a syncline with the Azurbajic quartzite and Siamose slate. So geology is also a predictive science, just like any other science, all right? You just don't look at things and go ooh-ah and start drawing lines on maps and colors and just make it all fit later. You can actually make predictive models. But anyway, I think that's it. Enjoy the scenery, and if you have any questions or comments, please leave them below, and I hope you learned something. Something interesting right here closer to the northeast end of the outcrop. You can see the gray wacky here. You can see a gray wacky bed here. Then you see the biff in between, and you can see how it's all following that nice trend, except the cleavage. But then there's this, kind of following the cleavage. Well, what is that? We have a mini fault here filled with basically quartzite. How do I know it's a little fault? Well, you see here, you see the plane, you can see there's some deformation here, and I have taken samples of this, and preliminarily, it looks like a quartzite. This is definitely quartz, this stuff. Here's where I took my sample, that's quartz. So, this was a clastic injection along the fault. How do I know it's a fault? Because here we have a bed of gray wacky here, and that bed continues over there. And as you can see, if this wasn't a fault, that bed would go up that way, or that bed would come down this way. And it doesn't, so we have a slight offset. We have an upside here and a downside here. This is definitely probably near the end of deformation, after metamorphism, all that. The cleavage had probably already developed at that point, which is stratigraphically. Then you have the iron. Then you have the Negaunee Iron Formation. When we go around the corner, it's... Yeah, beep, 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 beep. Insert geomap here. All right, hon. You can stop that. I'll take... For greens and grays. And whatever that was. Insert geomap. What were the dips there? I don't even remember. Well, that doesn't make sense. All right, let's go back. Did you see any birds in there, Sarah? Birds? Hello? Birds, are you there? Birds? Ghosts, goblins, spooks, specters? Anybody? Are you home? Aliens? Anything? Aliens?